Hello, everybody. Welcome back to another video. Start with a joke. Haha. Why can't a wizard proofread? He's only got spell check. Okay, let's get to it. So today is induction part 2. If you have missed induction part 1, go find my video. It is very, very similar. The process is very, very similar. The only difference, it feels different, but it really is the same thing. So I'm hoping that this works. Okay, here we are. Okay, so it's a mathematical induction for divisibility. It's a divisibility test. It uses a very similar process to a sum of a series proved by mathematical induction that 7 to the 2n minus 1 plus 5 is divisible by 12 for n is greater than or equal to 1. So hopefully, let's see if I can do this without a calculator. So first steps first, prove true for n equals 1. Okay, same as before. So it'll be 7 to the power of 2 times 1 minus 1 plus 5. That's going to be 7 to the 1 plus 5, which equals to 12. And then at this point here, that's basically for n equals 1, correct? Now we've got the answer 12. 12 is actually divisible by 12. And the way that we show that is just by dividing it by 12 and showing that we have a nice even number. So we've got that. Therefore, true for n equals 1. So now second step is the same as before. Assume for n equals k. And we'll write 7 to the 2k minus 1 plus 5 equals 2. Now I'm going to write 12a. That 12a means that it's divisible by 12. I can take 12 out as a common factor. Now this is going to be important because we're actually going to use this very, very similarly in our part 3, which is prove for n equals to k plus 1. So here we'll get 7 to the 2k plus 1 minus 1 plus 5. And I'll label this as 12b, again, showing that it's divisible by 12. Now, very, very similar to before, I'm going to try get something up here. Oh, that's going to help me substitute in, I guess, something down there. So the way I'm going to do this is let me just rewrite some of this. Let me clean up what we've got. We've got 7 to the, oh, you know what? Let's start over here because why not? So going with this line here, I'm going to say, I can see that 5 here is common. So I'm just going to say, okay, well then 5 is going to equal to 12a minus 7 to the 2k minus 1. Okay, so all I've done is I've rearranged the formula. And so what I can do now is I can rewrite this as 7 to the, I'm going to write this as 2k plus 2 minus 1. So this would be 7 to the 2k. And again, with the colors, it's important. 2k, that'll be plus 2, take away 1. So it's just going to be plus 1. And instead of writing plus 5, I'm going to write it as plus 12a, take away 7 to the 2k minus 1. Okay, equals to 12b. But in this case here, I'm just going to work with this. Okay, and I'm going to keep rearranging and seeing what I can get. So at this point here, I want these powers here to be the same. So the way I'm going to do that is plus 1 is actually significantly larger. So I'm going to write it as 7 squared times 7 to the 2k minus 1. Okay, hopefully you can see where that came from. All I've done is I've taken out 2 lots, because if I add these powers together, the 2 and the minus 1, it'll give me the plus 1. So I'm just playing with the indices laws here. And I've still got the plus 12a, and I've got 7 lots, or 7 of 2k minus 1. So now, if to rewrite this, 7 squared becomes 49 lots of 7 to the 2k minus 1. I'm going to move the 7 lots, 7 to the 2k minus 1 there, and I'm going to have a plus 12a at the end. And I can see here there's 49 lots of this, whereas there's only one lot of that. That's kind of the trick here. We want to make the powers here kind of even and something to work with. So that way we can kind of start to collect like terms. It's going to be hard to see it first, but as you do these more and more often, you'll start to see it. So 49 take away one lot. If you really want, you can kind of see it as that. One lot of 7. That's going to leave me with 48 lots of 7 to the 2k minus 1. And then it's going to be plus 12a. And to show that it's divisible by 12, all I got to do is take out a common factor of 12, which leaves me with 4 lots of 7 to the 2k minus 1 plus just a. Therefore, true for n equals k plus 1. And that's it. Therefore, true for all n is greater than or equal to 1. And there you go. Now, I could stop there, but I'm going to show you one more kind of technique. Again, this is somewhat lengthy, so if you need to stop the video, pause it, play it back, look over it again. This is one trick that I've come across that I haven't seen very often, may be helpful for you in the HSC, especially if your substitution, which you do from the assume to prove part, if your substitution isn't very clean and it doesn't seem to work out for you, there's this little trick here. So this question here I came across, and if you try to do this by substituting bits and pieces, you will not get there. Trust me, I've tried. My class has tried. Justin, that's you, buddy. But the way that we do this here is we apply this little kind of cheeky rule where if you go, and I'll actually leave this as an exercise. I'll say if you do f of k plus 1, take away f of k, this should also be divisible by 9 as well. So that's the trick here. And I might actually let you guys do that. Now, why that actually works is if you think about it, if we talk about numbers that are divisible by 9, if I say that this is, let's say, for example, 45 is divisible by 9 and 36 is divisible by 9, that means the difference will also be divisible by 9. Okay, I can pick whatever numbers I want. If I want to go another number that's divisible by 9, let's say that's 90, and I take away, let's go even 18, that'll leave me with 72, and again, divisible by 9. Okay, so it's just kind of this concept, but using this will actually allow you to help cancel out some gross unknowns or even some just gross expressions. This tends to work. Okay, so this will work for every divisibility question and is a good kind of second method to have up your sleeve if your divisibility isn't working out very nice. All right, I'll leave that there and I'll catch you guys next time. All right, bye-bye.